Today we're going to talk about Newton's first law and momentum. I'll write this here. Newton's first law. Newton's first law is also called the law of inertia because it describes inertia. Now, Newton's first law says that um, an object at rest will stay at rest, and an object at motion will uh, yeah will continue to remain in motion at the same speed and the same direction unless and until an external force acts on it. So I'll just clear this now. Yeah. So what is that law basically described inertia. Now inertia is the property of an object to resist a change in direction and motion and speed. Say you have a ball that is moving. This is 2 kg ball, and Newton figured out that inertia was proportional to mass and velocity. So you have this 2 kg ball here and another 1 kg ball here with this ball is with a mass of 2 kg and this one with mass of 1 kg, and you try to kick both of them. Obviously, this one will be harder to kick because it has more inertia. It will resist the change of motion more because of its mass. So this one will resist it more, and this one will resist it less. So that means this one will be easier to kick than this one. Now, what Newton found out was that he found out the formula for momentum, which is actually um, denoted by P, and that momentum is just a measure of inertia in motion. And now he found out it was proportional to mass and velocity, and the proportionality constant is 1. So we can say that P is equal to mv. Now let's come to Newton's second law. And in his second law, Newton described force to be the rate of change of momentum. Now, the rate of change of momentum can be described as the rate of the change in momentum delta p by time. And he found that to be proportional to mass, and he found it to be proportional to acceleration. So he devised this formula: F is equal to ma, one of the most important formulas in mechanical physics. And now let's try to find the unit of force. So the common unit for force is actually newtons, but we have to see what that really is. And now the SI unit for mass is kg, and into acceleration is meters per second square. So F is equal to kg meters per second square, and that's also considered to be 1 newton. And the definition for 1 newton is the amount of force required to push a object with a mass of 1 kg at 1 meters per second square. And remember that if it does not have any acceleration, that means it's traveling in a steady speed, it will not have any force because the acceleration is going to be 0 if v and u are the same, which is the final velocity and the initial velocity. So that means the force acting on it will be 0, like a ball rolling down a slope. there, if it's a steady speed, that means x, say the initial velocity is x and the final velocity is also x, then there will be no force acting on it. Yeah, that's it. Let's come to Newton's third law. In his third law, he says that for every actional force, there is an equal and opposite reactional force. This means that whenever two bodies interact with each other, there will be a reactional force between them. That means, like for example, you are on a boat here. I'm not a great artist, so please bear with me. Um, this is a boat, and this is the pier or the dock, and you want to come here. Yeah, so this is you. So the common thing you would feel is you would feel the boat going backwards, right? As you go forwards, the boat will go backwards. That is a very good example of Newton's third law because you are pushing back on this, trying to get here. If you push back, then you will go forward. That's what Newton's third law says. That's also how we walk. Otherwise, we wouldn't be able to walk. So if you are here, you exert a force on the ground, and the ground exerts a force back on you, and then you move forward. Otherwise, we need someone to kick us around every time, and that would not be good. So, Newton's third law is actually a very important law. But you can say that, so imagine a horse and a cart here. There are a lot of doubts you might have with this because, for example, say this is the cart and you have a horse. Uh-oh, I'm not really good at this. Yeah, I don't know what this is. Yeah, so you have a horse here. Okay, stop, bro. Now, scientists argued with this, devising a problem called the horse cart problem. This does not look like a horse, but we'll call it that for now. So they said that if the horse moves forward, then the cart will exert an equally opposite force backwards, and then they will stay in an equilibrium forever. And that's not what happens in daily life. So they argued that Newton's third law, I mean, might be wrong. And but that was not the case because here the horse exerts a force on the ground and the ground exerts a force back on the horse, which and the total net force of the horse is greater than the cart can pull. So the whole system, this uh, this horse cart system, it moves forward as a whole. And that's why um, a lot of students actually make a common mistake in this, thinking that the Newton's third law will create an equilibrium in both the objects. If that was the case, then no life would be possible. And yeah, that's it. So thank you for watching and please subscribe.